So instead of saying the universe is expanding, what about saying that it's expanding with respect to our clocks and rulers? We can be 99% sure that this is a true statement. We also know that it can be reversed. If we reverse it, we can say that our clocks and rulers are shrinking with respect to the universe, or that matter is shrinking with respect to the universe. But so what? If it's just a different way of saying the exact same thing, who cares? Well, if standard cosmology is correct, we should end up with the same conclusions, but inverted, right? Well, the results don't agree, which means either I'm wrong or there's something wrong with the Big Bang. And that's what this talk is about. So here's what we're going to do. We'll show how mass acts on space to cause it to warp, and show how this results in a force field. Two examples are given, one for the electron and one for gravity and anti-gravity. And we'll show how these end up as quanta, and finally present a theoretical curve that shows how the acceleration of the universe changes with viewing distance. First, we need to understand how we change reference frames from a matter-based frame to a space-based frame. This illustration tells us that the word static is relative to your choice of reference static. In each of these three cases, you'll notice that red lines are static with respect to each other, as are the blue pair and green pair. We can choose a line from case 1, 2, or 3 to define our reference static, and given that choice, the other two cases are dynamic. If we choose case 2 as our reference static, then case 1 represents a shrinking frame, and case 3 represents an expanding frame. These three pairs illustrate the qualitative differences that allow us to talk about distance, speed, and acceleration. And from the illustration, we can see that when the lines are the same type, we can use one of the pair as a reference length, and use that reference length to determine the magnitude of the given type. For example, in the green case, we can choose the top green line as the reference static length, and use it to measure the lower green line and say the lower green line is 2 units long. And that is objectively true. Yep, dimensions are relative too. This might seem like a bit of a leap, but a clock is still a clock, and we still use it to determine the magnitude of change. But here we're talking about abstract clocks. Obviously, the non-abstract clocks we use in everyday life are far more practical, but with abstract clocks, we can easily switch from one frame to another using geometric representations of objective observables that are easy to align with reality and require no inductive reasoning. And most importantly, it makes it easy to write a sum of velocities that include clocks. It makes time geometric, objective, and verifiable. And as you'll see later, it makes Einstein's relativity much easier to understand. And most importantly, it brings rulers and clocks into the physical model, where they are just as vulnerable as everything else is to the laws of physics. Now, if you're thinking about what you see, you might be thinking, this is just motion, and motion is a change in position with respect to time. You're clearly implying that time does not exist. And I'd say, if you stop all motion in the universe, what clock will continue to measure time? Would there be any aging process that could continue? The notion of time that we've been carrying with us for centuries is a very practical one, and we have come to the erroneous conclusion that time exists, and we've done so by assumption and induction, not deduction. In this talk, we'll do the science, the labeling, relating, and characterizing stuff that you and I can observe and agree on. But we'll be using these labels and relationships developed here to do a few mathematical deductions. No inductive reasoning. Now, in the animation, there are pairs of lines for two reasons. You can't determine magnitude without a reference magnitude or length, and you can't determine type without a reference type. For example, if I were only to tell you that a ruler is a line-like object, then two electrons could serve as the two distinguishable endpoints of a reference length. And if I measured the speed of light with this reference length and a standard clock, I would have to conclude that the speed of light is not even close to constant. This might almost seem like a reasonable expectation given that Einstein said there are no preferred frames, which implies there are no preferred rulers either. So what's wrong? Well, that's what this talk is about. Okay, first a bit of math. The cosmic sum. A line is bounded by 2 points. Call them A and B. These 2 points define two vectors. One points from A to B, the other from B to A. The sum of these two vectors is 0, and so the sum of all vectors in a vector space is 0 or null. And because the units are abstract, this sum applies to every type of vector, whether it's static or dynamic. Any vector can be used as a reference length. We really don't care where it's pointing. If we use it to measure something, we only need the magnitude part of the vector. But because a measurement is a proportion, we often don't need to explicitly use it as a reference object. The proportion of interest is often implied by its relationship to other lengths in an equation or its geometrical context. In the yellow equation, if we pull one vector out from the sum, we can see that for the total sum to remain 0, the two vectors must be equal and opposite. That is, for any single vector in the universe, it must be equal and opposite to the sum of all other vectors. We can change the size of these two vectors, but they must both change by the exact same proportion to keep the sum at 0, and that means we can't detect the change with only one reference length, which means nothing can get bigger without something getting smaller. And this applies to all subspaces or reference frames as well. That is, the sum of any subset of these vectors must also be equal or opposite to the total of all others. And by subspace, I don't mean the usual mathematical definition. This will become clear later. So let's do an example. We use the idea that time is really just a speed that we use as a reference speed to measure the magnitude of other speeds. But to show that time, speed, and velocity are interchangeable, we'll use the reference speeds just like velocities. Okay, so take a moving vehicle with a velocity v. Note that we're just calling it a velocity. It's really a vector we've separated from the sum, as are t sub 0 and t sub 1. So we're out in deep intergalactic space, each of us with our own glass spaceships. The ships are identical. We each have a ball that we throw identically across the ship to an opposite wall. The balls bounce off the walls in their respective ships and return each to their respective starting points. Now we give your ship an inertial velocity v and repeat the throws. T sub 0 is the vector of your ball as viewed by me. T1 is the vector representing my ball as viewed by me. And T0 is the resultant vector of your ship's velocity v and T sub 1. And that sum must be equal to and opposite to the sum of all vectors in the universe. The math works just like regular vector math with velocities, but because of the equivalence of time and speed, we're talking about both. So the sine of alpha is the opposite of the hypotenuse, t sub 1 over t sub 0, and that is the same thing as a square root of 1 minus the cosine square of alpha, and that gives us Einstein's gamma function. And it took all of 3 seconds to do it. The math says as you increase your speed, your clock runs slower, or t sub 1 approaches 0 as v approaches t sub 0. Notice where t sub 0 appears. It appears in the same place as c in Einstein's famous gamma equation, which says that light makes the best natural clock or unit of time. And for those of you who are math enabled, will notice that there is nothing to indicate that t sub 0 is constant. Well, it's not in an absolute sense. It's the vector that is equal to and opposite to the sum of all vectors in the universe. And because we can only talk about magnitudes as proportions, the proportion of that last vector to the total sum is always 1. Just to be rigorous, we can't say that it is constant, only the proportion. And because the units are abstract, the result applies to all rulers and all reference frames in the universe, accelerating or not. So in other words, if there is a length that is apparently increasing in size, then there has to be an equal but opposite change in the reference length. In the case here, v represents a dynamic length that is increasing in size. And that's all special relativity is. It describes the other relative changes that keep the cosmic sum at zero or null. Now, if one length is increasing, it doesn't actually change the size of the universe, only the proportion of the increasing length to the other non-increasing lengths. And when I say length, I mean both static and dynamic lengths, and length means the magnitude of vector. And so if the universe is increasing in size and it is measurable, there has to be an equal and opposite change, shrinking matter. So let's take a closer look. The cosmic sum I've just described is abstract. There are no numbers and no real object, no concrete units. And if you were Mr. Intergalactic Man participating in this project, you would go to your version of NIST and give us all of your standard constants, and you'd tell us what units you use so we could relate all of your numbers and units to our numbers and units. But since you're not Mr. Intergalactic Man, we'll have to use our matter-based constants and units from our version of NIST. And we can do that since the equal but opposite rule implies that our measurements are equal but opposite counterparts to Mr. Intergalactic's. By the way, if you know what metric expansion means, you might be thinking that the metric of space-time is what determines length, not rulers. You might want to think about how you can determine a metric without measuring. And how would you show that space has an intrinsic metric if you can't modify the curvature of space? And if you say you can do this with mass, then you have to show how mass acts on space, or vice versa, to cause it to curve, which is what we'll do now. Okay, so now we'll look at uniform expansion and follow the logic. In the diagram you see two lengths, L and L prime. You compare L prime to L, and the first time you do, you find that they are the same length. The second time you compare them, you find that L prime is now twice as large, as shown in the figure. You cut out a piece from L prime that's equal in length to L. You compare that piece with L, and again, it is twice as long. That is, it was equal in size when you cut it out, and then grew to 2 times as big. Notice that I did not say with respect to time. This is the uniform part. It doesn't matter which piece you cut out or what size you cut out. The same thing happens. It doubles in size. Our measured change is the proportion L prime minus L over L. So if your static reference length is a meter and reaches from A to C, then with a measured change equal to 2, C prime will be at 1 times 2, or at 2 meters. So that's the static part. So far we've been talking about differences in length as if we were talking about two separate lengths rather than a single changing length. Now, because the length of interest is changing, we need to measure it with a reference change, a clock, and that gives us a magnitude or rate of expansion, the equivalent of Hubble's constant. The meters cancel, and it's expressed as meters per meter per second in SI units. Hubble's law says that the further away from Earth you look, the faster space and its content is receding from us. But Animation 1 says there really isn't a difference between space and time. They are two different measuring contexts of the same thing. So if length is expanding, then so is time, or speed. Remember, time is a reference speed. I think I might have said that once before. We can see this more clearly in this slide. We take a length r that changes by some amount dr and a velocity v that changes by dv. But because these are really two different aspects of the same thing, the proportions that they change by must be equal. So we write them both as a proportion of s and as a sum. SR equals r plus dr and SV equals v plus dv. And since we can solve each for the same identical proportion, we can equate them through s, and s goes away. By the way, if you're really concerned about following the math, you may want to pause the video and get a closer look. And if you really want to get serious, I have PDFs of this talk on my website, http www.designerscience.com. So we solve for s in each equation and equate, rearrange, and we end up with VDR is equal to RdV, the violet equation. We measure, we divide the changes, dr and dv by dt to get the magnitude of change, and that gives us the rate at which space is accelerating. This acceleration looks exactly like that of uniform circular motion, but it's not. They are equivalent. But what this says is that because the acceleration of uniform circular motion is identical to the expansion or contraction of a frame, we can balance our cosmic sum with circular motion and or contraction. Oh, and before I go on, I want to point out that this looks exactly like the acceleration of uniform circular motion because there are two vectors that change together in exactly the same proportions in both cases. For circular motion, the change in the velocity vector and the radius vector is purely angular. They both change by the exact same angular proportion. In the case of expanding or contracting space, the change is strictly in magnitude. And I should point out too that Hubble expansion is rectangular. That is, in this kind of expansion, a rectangle remains a rectangle. For contrast, if all points of a rectangle were to recede from its center with a constant velocity, it would eventually become a circle. This is just another way of viewing Hubble's law and the consequence of the constant slope of v with respect to r. And here we just use similar triangles to find the same acceleration of the expansion of the universe. We can use this figure to deduce Hubble's law as a function of the slope dv dr. It's a constant slope with units of per second. Okay, to recap what we have so far. We have Hubble's law, which represents uniform rectangular expansion, and because we can't separate space and time, they must change as one. Space is space, whether it's expanding or not, but when the change is observable, we can measure that change with a reference static and a reference change, a ruler and a clock. And so a single line that is expanding with respect to a reference static needs at least two reference objects to measure it correctly, and so has at least two dimensions. These are embedded dimensions: objective, observable, and verifiable. Classical time is not verifiable. We have separated matter-like frames from space-like frames. That is, rather than have a single space-time, we now have two space-times. Each are static with respect to themselves and dynamic with respect to each other. Galaxies that are at rest in the expanding frame are at relative rest, and that allows us to say space isn't expanding, matter is shrinking. And now we can really dig in. To get the symbols right, I use r to represent the distance from the center of a measuring frame and r prime as the distance in the frame that is expanding or contracting, the dynamic frame. A is a contracting frame's acceleration. H is the equivalent of Hubble's constant, but it's not necessarily the rate of expansion of the universe. I use h sub 0 for that. We know from Einstein's special relativity that as your speed increases with respect to some frame, your clock will run slower than theirs, and that the length in your frame contracts in the direction of motion. And this is what we have to incorporate into Hubble's law. We start with Einstein's equation for length contraction and replace the v with hr prime. The primed length is the one in motion with respect to our matter-based frame, and so it's the one whose length contracts as its velocity approaches the speed of light. We do some algebra, solve for r prime, and come up with equation 1, the pale yellow equation. If you want, you may want to get out some paper and pencil and follow along and verify the math for yourself. We will come back to this equation in a bit. Now, we put this new value for distance into our equation for acceleration. Since v is equal to hr prime, we can substitute it for v in a equals v squared over r to get a equals the quantity hr prime squared over r. And then using the relativistic length contraction for r prime, we get a value for relativistic acceleration due to a contracting frame. Acceleration a is equal to h squared times r times c squared over the quantity c squared plus h squared times r squared. Let's call this the blue equation. If we take the limit as r approaches infinity, the c squared in the denominator becomes relatively small and can be dropped. And so the h squared cancels as does an r, and you have the maximum possible acceleration in the universe for a single frame. So when r is 0, the acceleration is 0, but the function is well behaved since we have c squared in the denominator. When hr is small relative to c, then we can drop h squared times r squared from the denominator, and you have a is equal to h squared times r. It's worth noticing that this looks exactly like uniform angular acceleration and is also the derivative of Hubble's law with respect to time. And the most important feature of this equation is that when hr is equal to c, this is a maximum of the function, and it is because of this maximum that we can calibrate it to real matter. It represents the best natural choice for a natural unit of length and time. We'll come back to this in a minute. Before the impact of this can be understood, it needs to be put into a measuring context. So now, how would we know if we were to run into a shrinking frame, and then how would we measure it? Clearly, a unit of length in an expanding frame is different than one in a frame it is expanding with respect to. What to do? You measure it in a modeling context. Yeah, we're not quite ready to try it with real clocks and rulers, so we'll use a model. To model a measurement, we write it as a quotient of the two magnitudes of interest. The result is a scalar, the measurement result. You can also write this as a product, the scalar times the thing we measure with, where the thing can be a boot if you want. As a model statement, we really don't care, but we do want to separate the semantic part from the thing it refers to. That is, when we measure something, we are encoding an observation into an abstraction, and it is the abstract stuff that we want to work with. That's the math. So, in our two reference frames, we measure the same agreed upon unit of length using our previously agreed upon reference lengths, and we end up with something that looks exactly like unit conversion, and well, it is, but it's not. If I take a meter and compress it to a foot in length, I can do unit conversions from meters to feet, and it would be correct as far as the units go, but why would it occur to do the same to time? Unless you knew you were measuring length in a compressed frame, it wouldn't make sense. But since we know that unit conversion for time is required as well as conversions for every other dimension, we need to include those as well. But for this talk, we'll just include references for length, speed, velocity, and acceleration. And just note that if a frame is not compressed, your meters will agree, you don't have to worry about it. But if it is a compressed frame, then we need to change our units of time to match the compressed units. And more importantly, since we are comparing the same unit in compressed and not compressed frames, we are looking at a relatively dense space from the outside, so it's not just unit conversion. Okay, so one of the most remarkable things about special relativity is that when units of length and time change, mass changes as the inverse of the change. The same thing happens here with dense space. And because it varies in exactly the same way as mass does in Einstein's equations, we can treat spatial density exactly as if it were mass. In fact, as you'll see, it's impossible to separate them. So now incorporating this idea, we can write out an equation for the force generated by shrinking matter with respect to space. This equation is what acceleration looks like when it results from warped space-time. To get a feel for this equation, we'll go over a few features. When we take the limit as r sub 0 approaches infinity, we end up with mc squared in the numerator, and that looks an awful lot like Einstein's E equals mc squared. But let's look closer. Work or energy is defined as a force acting over a distance, so when we calculate this over a distance from 0 to infinity, we end up with equation 3, with E equals m sub 1 times r sub 0 times c times h times pi over 2. And when we choose hr sub 0 equal to c, the natural unit for time, we end up with something that looks like Einstein's h bar f equals mc squared, where h bar is Dirac's constant, or a reduced Planck's constant. F is the frequency, m is the mass of the particle, and c is the speed of light. In other words, it seems that not only does force emerge from the geometry of warped space, so does energy. The warped space part sounds a lot like gravity, but it's not. It is, but it's different. This is telling us that force and energy in general comes from warped space-time. Going back to our original assertion, that space is static and matter is shrinking with respect to space. We first need to establish that we are in fact talking about matter, and this establishes that fact. And in a minute we'll show how this also correctly represents gravity, but in a slightly different way. So now we take the limit as r sub 0 approaches infinity and end up with a very simple inverse square law that looks like Coulomb's law for the force between two electrons. And when we plug in the mass of the electron and the speed of light in SI units, we get an exact match for the classical radius of the electron, which is good, but not complete without a value for h. But we can do that now that we have a value for r sub 0. We just use equation 42 and solve for h. Calculating h gives us an expansion rate of about 10 to the 23rd per second. We're almost done now. We assemble m sub 1, r sub 0, and c to create our version of h bar. We call it rho. And since my version is identical to h bar f equals mc squared through mc squared, we equate them and solve for alpha, the fine structure constant. This number, alpha, has been a deep puzzle for decades. Feynman called it a magic number because he nor anyone else could figure it out. So this is what's happening. Let's say you have a nicely marked ruler with a single hash mark at 10 to the minus 13 meters. Call this r sub 1. Let's also say you have another ruler just like r sub 1 but with a hash mark at 10 to the minus 15 meters. Call this one r sub 0. You line them up and give r sub 1 a contracting velocity of 10 to the 23rd per second. The hash marks will line up, and at that point of lineup the contraction velocity will be so close to the speed of light you can't measure any difference from the speed of light, but it will be slightly less. And that's all alpha is. It's the ratio of these two numbers. But alpha always pops up in equations related to the absorption and emission of light, right? Well, remember we are talking about curved space-time, and that is what Einstein found, that gravity is curved space-time, and so we can expect the equivalent of a gravitational redshift from an electron, or a wavelength emitted from an electron will expand to ambient space compression, or light that leaves an electron compressed will arrive uncompressed by a factor of alpha. To show this, we go back to equation 1 and plug in the value of the reduced Compton wavelength and compute the classical radius of the electron to an accuracy of about 3/1000ths of 1%. And it's off by that much because hr sub 1 can never actually reach the speed of light. With this understanding, we can integrate the redshift into rho to show that the resulting constant is a universal constant for any mass. But verifying this could be beyond technical reach since it's almost impossible to measure light radiated by a single naked electron, and you would have to do that. And if you use stable matter, say hydrogen, the electron interacts with the proton. And given that an electron has this spatial gradient, just like gravity, you can expect similar properties. One of them is that clocks run slower as force increases or as you get closer to the center of the mass, and the factor by which clocks run slower is also the redshift factor. To illustrate the problem, say I have a planet 1 and I'm on the surface where my clock runs 1/2 as fast as the same clock infinitely far away. Then I bring in planet 2. It has a time dilation or redshift factor of 1/4. I position it just above my head where I have the combined effects of both planets affecting my clock. The net slowdown is 1/2 times 1/4 or 1/8 the speed of the infinitely far away clock. So if I turn on my flashlight and point it at an observer infinitely far away, she will measure a redshift factor of 8. The same thing would have to apply to an electron near a proton, but exactly what that factor is, I don't know. To get that, we need a complete model of an atom based on relative expansion. But the general idea suggests that redshift should increase when light is emitted from matter of higher density and decrease with lower density or hot matter. and a decrease in alpha has been observed at energies over 80 billion electron volts. Okay, so now on to the finale. Figure 1 tells us that once the product HR prime gets near the speed of light, R prime virtually stops increasing in length, but not quite. For every R, there is still a value for R prime, but because it is virtually constant after HR equals C, the surface area of the surrounding sphere is constant for all R. In other words, the surface area does not increase as R increases, and so the density of that surface area decreases proportional to the inverse of R squared. This says that the inverse square law for gravity is correct only for R greater than the calibration radius of the gravitating matter, but we can still do some simple calculations for R greater than or equal to the calibration radius. This slide shows us that you can equate equation 2, the great equation, to Newton's equation for gravity. We cancel m sub 1 and drop the subscripts, and since our calibration radius is also where we'd expect the event horizon to be, that is, where the rate of descent is the speed of light, we set HR to C. Do some algebra and solve for R. And we get the Schwarzschild radius for a black hole. Now, the preceding discussion about redshift works here too, and in this context says that the event horizon actually does not exist as is often described. That is, nothing can travel at the speed of light, but it can come close. And the reason a black hole is black is because light emitted from a black hole is redshifted so much that the wavelengths of the light are close to infinity. But this radius is important in that it establishes a physical unit of length that can serve as a reference to measure other lengths to determine if a space is dense or not. The electron and black hole both share this same physical feature, and so we can take a look and see how they compare. And we get Planck mass, and why we do is very clear, but this is Planck mass over the square root of 2. The original Planck mass doesn't have the square root of 2, but that's okay. Planck mass comes up in theoretical physics pretty often and is believed to be important in quantum gravity. If you'd like to know more about it, I recommend Wikipedia. And just to show that h squared r as the inward acceleration of matter also works here, we'll calculate Planck length. Take the usual Newton equation for gravity, cancel an m and substitute A equals hr, and then for the remaining mass we substitute h bar h over c squared for mass. And h cancels and we replace hr with c, which defines our calibration radius, and solve for r and get Planck length. And I wish I had more time to discuss this, but alas, time is limited. So, as stated earlier in our cosmic function, the sum of all outward accelerations must equal the sum of all inward accelerations. Now, I won't show it here, but you can look it up if you want, that a random distribution of gravitating bodies can be treated as a single point mass, its center of gravity. So we take the Earth as a center of that point mass and calculate the mass of the universe. And here h is the value of Hubble's constant as measured by WMAP. And we get an estimate of about 2 times 10 to the 53rd kilograms, an error of about 41%. But what's interesting here is that the model predicts less matter than has been measured. In fact, most observations tell us that there is not enough matter to account for a few of the gravitational effects that we observe today. The dark matter phenomenon. I won't go into the historical details here, but if you want to investigate further, I've provided a few links below that should help. And if you're thinking the Earth is not the center of the universe, you're right. This applies to any location in the universe. So what's up with this discrepancy? What about dark matter? I'll just tell you here that the answer comes from n spaces. That is, because the space-time of the universe is not singular, we have to account for the motion of all spaces with respect to all other spaces. I don't want to go into this here, but there are about 1,000 other tangents too that I could go into more detail on, but I do have to save some stuff for my book. But here's a hint, and I emphasize that this is just a hint. Think of a spinning universe that contains one spiral galaxy, and then embed that within our universe. So if this theory is right, then what we should expect is that the acceleration of our expanding universe should slow down in a very predictable way. You can see here that the acceleration reaches its peak at about 14.7 light years out and then changes from increasing to decreasing. Unfortunately, because of the extreme redshift, we'll never be able to detect the negative part of this curve. But we should be able to eventually detect the slowing of the acceleration by measuring the recession velocities of the galaxies that are currently out about 4 to 8 billion light years. And I'm going to guess that that technology won't happen for at least another 10 to 15 years. But verification still might be within reach now, and I would love to tell you about it, but again, I do need to save some stuff for my book. So to summarize, dimensions are relative too, which really means context matters, and really this whole talk is an analysis of the context that underlies the physical nature of the fundamental constants. Take the number pi and ask a physicist and they'll tell you it's unitless, but it's really pi diameters equals 1 circumference. The units are diameters or circumference. Think about it. And classical time does not exist. Arguments that it is an orthogonal dimension are pointless if it can be expressed in a way that is verifiable and equivalent. Special relativity can be derived without light speed. For those of you who know SR know how much I have not said here, but I guess I really should do another video on this one, or maybe you can. Gravitation and electrons can be derived from special relativity. Yep, and anti-gravity as well. That comes from the equal but opposite rule, and that's what the expanding universe is, anti-gravity. The universe is a composition of n-parallel quantum space-times. Also something I need to do another video on, since this goes into light waves and particles. You can call one of these a quantum subspace or whatever else works. I kind of like Smarterion. There are other things that follow this idea as well, but not so easy to present yet, and some I'm still working on. A model of a measurement tells us how to anchor the physical to the abstract to get objective and universal natural units. And again, context matters. The electron is a single space-time, and it's perfectly spherical, as you might have guessed. Going from a rectangular space to a spherical space must mean it's spherical. Mass comes from relatively dense space, which is apparent when you look at the maximum peak in figure AOOU. That peak completely determines the function, and that is what we measure when we measure mass. Speed is the only known thing to cause curved space-time. Some scientists believe otherwise, but belief isn't science. The universe is steady state. I'm sure I'll get branded as a crackpot for this one, but that is where the logic leads. And for those of you who are thinking that my cosmic sum only works for the sum of all momenta, yes, that's correct for massive objects. But ask yourself, where does mass come from? The Higgs field? Well, as I have said before, context matters, and quantum mechanics has its own context. And that context is radically different from in subspaces. There is no dark energy. What we have been thinking is that since the acceleration of the universe has been discovered, that there is this huge mass being pushed outward. That is, that there is work being done in moving the galaxies outward. Well, I do hope I haven't made a mistake, but it looks to me like it's better to say that the galaxies aren't moving, matter is shrinking. And if you were listening between the lines, you probably have inferred that this research is very fundamental. It comes from an effort to do physics from scratch, going back to the first thoughts of our ancestors, where we learn to represent what we observe with paintings on the walls of caves. So if it seems simple, that is partly why. There are other reasons too, but that's quite another can of worms, and I'll leave that for now. And finally, this talk and my research is supported by yourcosmetics.com. If you find this kind of research of value, please go find something there you like and buy it. Buy lots. The more you buy, the more time I can devote to my research. Thank you for your time.